Hello students, today in solid state chemistry I am discussing another one important concept, that is defects in solids or imperfection in solids. Defects or imperfection in solids. As friends, here we already learned the two types of the solids. There is a crystalline and amorphous. In crystalline solids, there is an orderly arrangement. Okay, the arrangement of the constituent particles, the particles, atoms, ions or the molecules, they are arranged in an order. For example, if I take a crystalline substance like AB, so where the arrangement in that crystalline compound is a order, there A, B, A, like this, B, A, next B, A, B, A, B, A, B, A, B. This is an orderly arrangement of the constituent particle in a crystal lattice. Okay. So, but there is some defect during the formation of that crystal. Okay. So, that defects we call as an imperfection in solids. If any disturbance is done in the orderly arrangement of these constituent particles, any disorderness is observed in the crystalline compounds, so then that solid or that compound is called as a defected. There is an imperfection in the solids. Let me define the defects or imperfection in solids. Any disorder or any disturbance in the orderly arrangement of the constituent particles in a crystalline substance. Okay. So that is called as a disorderness or the defects in crystals. As stands here, mainly there are two types of the defects. One is point defect and another one is the line defect. Point defect and another one line defect. The defects are classified into two types, point defect and line defect. Instance here, the point defect means the disorderness is observed around a lattice point. That is called a point defect. For example, so say let's now have to A, B, A, B, A. So B, A, B, A, B. So this is the arrangement of constituent particles in crystal lattice. Okay. It's in a perfect crystal where all the particles are orderly arranged, creating a forming a three-dimensional crystal lattice. So they are orderly arranged. So it is in a perfect crystal. Okay. If some lattice points are vacant, for example, there are at some lattice points no particles will be formed, no atoms will be formed. Okay. So this defects around this lattice point. So there is a one particle is missing from its lattice point. So then we call it is in a point defects. That means the imperfection at a lattice point. Okay, there is a point defect. If a complete row is missing, then we call it is a line defect. For example, so this is a long range arrangement. After a certain distance, if the complete this row is missing, okay, so complete this row is missing, so then we call it as a line defect. Okay, there are two types, point defect and another one is the line defects. So in point defect, the defect is observed around a lattice point. Okay, there is a missing of some particles around a from its lattice point. So there isn't a point defect. So in line defect, a complete row is missing. So that means the atoms or the constituent particles from that row, they are completely missing during the formation of that crystal lattice. So that is called as a line defect. Like that, there are two types of the defects. Here students, the point defect is very important. Let me go with a point defect first. In point defect, again it is classified into three types. One is stoichiometric, defect, and another one is the non-stoichiometric defect. Stoichiometric defect, non-stoichiometric defect, and third one is impurity defect. Like that, we classify this point defect into three types: stoichiometric defects, non-stoichiometric defects, and impurity defects. Okay. So these all are the point defects. We are not studying about the line defects in class 12. It's because it's limited to only for point defect. Okay. So point defects are stoichiometric, non-stoichiometric, and another one is the impurity. First, let me define these types of point defects. So here first, stoichiometric defects means, so this is the one type of defects where the stoichiometric ratio of the constituent particles is disturbed. So that means it not remains same. The stoichiometric ratio is disturbed. For example, initially, let me say there is 100 particles of A and 100 particles of B. Okay. So there is one solid crystals made up of AB elements. So where 100 particles of A and 100 particles of B, they are in the ratio of 1:1. So this is a compound. After the defect, if there are some particles are missing, so some particles are missing from an A element and some particles are missing from B element. Okay. So that the final stoichiometric ratio between A and B is, it is 97 and B is also 97. Okay. Now the ratio is also same. Here is also 1:1. Before defect also it is 1:1. There is no disturbance in the stoichiometric ratio. That means the stoichiometric ratio of the constituent particles is undisturbed. Okay. So such a defect we call as a stoichiometric defect. Okay. So stoichiometric defects, the ratio of the constituent particles, or ratio of the ions, or ratio of the atoms. Okay. So that is undisturbed. That is called as stoichiometric defects. And since here in non-stoichiometric defects, this ratio is disturbed. Say initially the crystal, we are expecting the crystal contains 100 A particles and 100 B particles, but there is some defect in that crystal. So then the crystal contains 97 of A particles and 99 of B particles. So here the ratio is not same. That means the stoichiometric ratio is disturbed after that defects. So such defects we call it as a non-stoichiometric defects, where the stoichiometric ratio of the constituent particles is disturbed. It is a non-stoichiometric defects. And the third one is an impurity defect. Okay. Impurity defects means this defect arises due to the presence of impurities. This we call as an impurity defect. Okay. Now I will study in detail about these three types by taking a few examples. With the first one, the stoichiometric defects. And since here, stoichiometric defects, again, defects. In stoichiometry defects again is classified into four types. One is vacancy defect. Second one is the interstitial defect. Third one is Stoichiometry defect. Fourth one is the Frankel defect. Like that, there are four types of the defects, four types of stoichiometric defects: vacancy defects, interstitial defect, and Stoichiometry defects and Frankel defect. So vacancy defects and the interstitial defects, therefore these two defects fall in non-ionic compounds or non-ionic solids. And Stoichiometry defects and the Frankel defects, therefore they are for ionic compounds. Vacancy defects and interstitial defects, they are observed in non-ionic compounds. Non-ionic compounds means where the constituent particles are either atoms or the molecules. And Stoichiometry defects and Frankel defects, they are observed in ionic compounds where the constituent particles are ions. Now, let me go in detail about these defects. First, let me study about the non-ionic compounds. So non-ionic compounds is the vacancy defects. So students, in vacancy defect arises because of some of the lattice points are vacant. Okay, this simply we call it a vacancy defects. For example, these are a crystal which contains constituent particles. I am showing the constituent particles with this circle. So these are the constituent particles, they are atoms or molecules. So this is a perfect crystal. If some of the atoms they are missing from their regular lattice point, so this point is vacant and this point is vacant. So that means there are some lattice points are vacant. Okay, there shows the absence of atom in this position. Okay, so such defects we call as vacancy defects. Right? So if some lattice points are vacant, that is called as vacancy defects. And students, here in vacancy defects we observe another one. This is the definition of vacancy defect. Vacancy defects is in one of these stoichiometry defects in which some lattice points are vacant. Right? So in that crystal, so that is called as vacancy defect. And the another one is the density of this vacancy defect. See, how to find whether that non-ionic compound has a vacancy defect. Okay, so for that, just measure the density. So density, if density decreases, then it is called a vacancy defect because some of the lattice points are missing. That means some of the atoms are missing from their regular lattice points. So the density decreases. So then it is a vacancy defect. And next, another one is the interstitial defect. Interstitial defect. As says here, in interstitial defect, what happens? Let me take the same crystal. Okay, so this is the perfect crystal where all the constituent particles are orderly arranged. Okay. But now, so there is some defects in that crystal. Okay, that defect is an interstitial defect. So what happens in interstitial defects is some of these atoms, they are not present at the regular lattice points. Instead of that regular lattice points, they occupy some interstitial site. For example, this particle this atom is not present at their regular position. Instead of that, it will occupy a interstitial position. So interstitial position or at interstitial site. This atom is present here. Okay. So interstitial position or interstitial site means this is the empty space present between the two rows. Okay. This is the empty space present between the two rows, that is we call it as an interstitial position. So here the constituent particles, they are not present at the regular lattice point, they occupy the interstitial position. Okay. So such defects we call it as an interstitial defects. Okay. In vacancy defects, the complete removal of that atom from the crystal lattice. Okay. Whereas in interstitial defects, they are not completely removed, but those atoms will occupy a interstitial position. They are present at the interstitial position, means they are present at the empty space present between the two rows. This interstitial position, and such defects if you observe, then that is called as an interstitial defect. Now, how to find whether that crystal is having an interstitial defects or not? Okay, so for that, just measure the density. See, density of this crystal. So density of the crystal, it remains same. It remains same, not change, because the particles are not completely removed from that crystal. Instead of that, they occupy some interstitial position. The particles are present in that crystal only. They are not completely removed. Therefore, the density remains same. If the density is same, even after that defect also, then it is an interstitial defect. If density is decreased, then it is an vacancy defects. So now let me go to the next concept, that is next students, the another one type of stoichiometric defect is Schottky defects. Schottky, it is also pronounced as short key or Schottky defect. Schottky defect and another one is the Frankel defects. So these two defects are observed in ionic compounds, and these two defects are same as vacancy defects and interstitial defects. Okay. So vacancy defects is for an non-ionic compounds, whereas the Schottky defects is for an ionic compound. Similarly, interstitial defects is for non-ionic, and Frankel defect, the next one, is for an ionic compounds. Okay. Now, let me go with this one. The definition first. Schottky defects. See, in Schottky defects, let me take an example as NaCl, sodium chloride. Okay. Let me draw the NaCl structure, crystal structure. Okay, so here, say Na plus, this is Cl minus, Na plus, Cl minus, Na plus. So, just taken one crystal, sodium chloride crystal. So, this is the arrangement of the constituent particles in a sodium chloride crystal. Sodium, then chloride, sodium, then chloride is in a they are arranged in a three-dimensional manner. So, same arrangement is seen in a three-dimensional manner. Now, what happens in Schottky defects is, so some of the cations and some of the anions are missing during the formation of that sodium chloride crystal. So during formation of a solid sodium chloride crystal, so some lattice points are vacant. For example, the sodium, it is missing from their regular lattice point. Similarly, the chloride, is also missing from the regular attachment. So these two positions are vacant. Okay. So here one sodium atom is missing. Similarly, one sodium ion is missing. Similarly, one chloride ion is also missing. So in Schottky defects, the equal number of cation and anions are missing from their regular lattice point. That defects we call as Schottky defects. Same number of the anions and cations are missing. If 10 sodium ions are missing, means there is 10 chloride ions are also missing. So that's why we define the Schottky defects as equal number of cations and anions are missing. So which maintain a electrical neutrality of the crystal system. The electrical neutrality of that crystal. So crystal is electrically neutral. So equal by missing the same number of cations and anions. Now students, the density, how to find that? How to find that crystal contains a Schottky defect. Okay. That an ionic compound is having a Schottky defects. Okay, so for that, measure the density. Okay. So if the density decreases, then that defect we call as Schottky defects. Okay. So this is an important. Let's concentrate on Schottky defects. In Schottky defects, the equal number of anions and cations are missing from the regular lattice points. If 100 sodium ions are missing, is 100 chloride ions are also missing, and the density of this crystal is decreases. If the Schottky defects is present in that crystal, means so density decreases, and this is observed in case of the compounds whose size is equal. Okay, equal size of cations and anions. Okay. So this type of the defect is observed in the ions which are equal in size. Okay. There is not large difference in the size of anions and the cations. Okay. Almost they are nearly equal. Okay, just copy it. Next students, another one type of the stoichiometric defects is the fourth one, Frankel defect. This defect is exactly same as the interstitial defects. In interstitial defects, some of the atoms they occupy an interstitial site, or they are present at the empty space present between the two rows. In Frankel defect is also the same. Okay. So that's why the Frankel defect is also called as a dislocation defect, because the constituent particles they are dislocated. Okay. To explain that, let me take an example as AgCl, silver chloride. Okay. So the arrangement of AgCl here is, so this is Ag plus Cl minus, then Ag plus Cl minus, so then Ag plus, so Cl minus, so here the Ag. And next Ag plus, so this is Ag plus Cl minus, then Ag plus Cl minus, Ag plus. So now this is the silver chloride crystal. Okay. So where silver chloride, this is the arrangement of the ions in the silver chloride. And since here in Frankel defect, what happens is there is a large difference between the silver and chloride ions. Okay. So cations, usually we know the cations they are small in size, whereas the anions they are large in size. Okay. So here the silver ions they are small in size. So during the formation of that silver chloride crystal, some of these silver ions, they are not present at their regular lattice points. Instead of that, their regular lattice point, they occupy a empty space present between the two rows. For example, this Ag plus ion is not present at this position. Instead of that, it will occupy a empty space present between the two rows here. Right? So it dislocated. So instead of this point, so it is located to here. Right? So that position is called as an interstitial position, and such defects we call as a Frankel defect. There is a definition. Right? So we can define this Frankel defect as there is a cations, they are small in size. Right? So these cations, they dislocated or they are missing from the regular lattice point. They occupy a interstitial position. There is an empty space present between the two rows. So here, so such defects we call as Frankel defects. And how to find whether that ionic compound has a Frankel defect or Schottky defect? Again, go with the density. So find the density of the Frankel defect. Okay. So density of Frankel defects is the density remains same because these constituent particles are not completely removed from that crystal system. Okay. Instead of that, their regular position, they are present at their interstitial position. They are not completely removed from that crystal system. Therefore, the density, it remains same. Density of the Frankel defect is remains same. Density will not change. Right? So this is about the stoichiometric defects in that Frankel defect. And second, let me tell you about this Frankel defect. It is also called the dislocation defects. And students, all these defects, they are also called as thermodynamical defects. Okay, because these defects arises during the formation of that crystal. And also this arises due to the heating also. Next, let me go with the next one, is the non-stoichiometric defects. Next students, another one type of defects is non-stoichiometric defects. Just now we learned that stoichiometric defects, there are 4 types. So there is the vacancy defects, interstitial defects, Schottky defects and Frankel defects. Now the next one is the non-stoichiometric defects. In stoichiometric defects, the stoichiometric ratio of the constituent particles is undisturbed. But in the non-stoichiometric defects, the stoichiometric ratio is disturbed. So as I told students, in non-stoichiometric defects, if that crystal is made up of 100 particles of A and 100 particles of B, if the defects is found in that crystal and the constituent particles, A particle, they are of 99 and B are of 98. So here the stoichiometric ratio is not same. Stoichiometric ratio of A and B, they are not same. Then such defects we call as non-stoichiometric defects. In non-stoichiometric defects, the stoichiometric ratio is of the constituent particles is disturbed. Okay, there is a definition of non-stoichiometric defects. Now, in non-stoichiometric defects also 2 types. One is the metal excess defect and another one is the metal deficiency defect. Metal excess defect and metal deficiency defect. See, metal excess defects, so in this defect the metal ions are more compared to the non-metal ions. So metal deficiency defects, so here the metal ions are less compared to the non-metals. Okay. So metal ions normally we represent with a positive, so metals are electropositive in nature. Okay, so before that sodium chloride crystal, let me give you an example. So for example, A, B is a crystal. Okay. So this crystals contains 100 A and 100 B ions. So where A is in a metal, B is in a non-metal. After the defect, we found that the total number of A ions are same. So A ions remains as 100 only, but the number of B ions, they are reduced to, so say 92 or 93, sorry, or 97. Okay, there are 3 B ions, that is these are the non-metals. So this is a non-metal and this is the metal. And so number of non-metal ions are decreased. So in that defect, the number of metal ions are more compared to the non-metals. So such defects we call it a metal excess defect. Right? And in metal deficiency defects, the A metal ions are less. Say initially they are 100 and 100, metal ions are 100 and non-metals are also in 100. And when the defect is observed in that crystal, so the number of metal ions are reduced to 97, where the non-metals remains as 100. So here, compared to the non-metals, metals are less, metal ions are less. Therefore, such defects we call as a metal deficiency defect. Now, let me go in detail about these two. So first, metal excess defect. Instance in metal excess defects, to explain that, I am taking one sodium chloride crystal. Okay. So this is the arrangement of sodium and chloride ions. Taking example here as NaCl. So number of sodium ions and chloride ions, they are in the ratio of 1:1. Now says in this sodium chloride crystal, when it is heated in the atmosphere of sodium, that means this sodium chloride crystal is heated in the presence of vapors of sodium. So here I am passing the vapors of sodium. This complete sodium chloride crystal is heated in the vapors of sodium. So sodium vapors means it contains sodium atoms. Okay, so it is heated in sodium vapors. So it is surrounded by sodium. So this sodium chloride crystal, it is surrounded by sodium atoms. Now, what happens when we heat this sodium chloride in sodium atmosphere? Some of the chloride ions, some of these chloride ions, they dislocated. So they escape from that regular position. The regular position and they are missing from the regular position. So the chloride ions here comes above that surface of that crystal, and the sodium atmosphere contains sodium ions. So this sodium ion, it loses one electron and forms sodium atom loses one electron and forms sodium cation. Okay, so this sodium cation and the chloride from that crystal, they react and forms a solid sodium crystal. So these chloride ions, they dislocated and they react with the sodium ions. So sodium ions from that sodium atom. So this sodium atom forms sodium ion by losing one electron. So sodium ion and chloride ion forms sodium chloride. And this electron will occupy this anionic site. So electrons will occupy this position. Okay, so let me show you another curve. So this electron will occupy a anionic site. Okay, the electron is present here. Now, like that, there are few chloride ions, they are missing from the regular lattice points, and that position is occupied by electrons. Now, compared to the metal ions, non-metals are less. Compared to the metal ions, non-metals are less. Before that defect, the total number of metal ions are more, but metal and non-metals are same. But after that defect, one of the non-metal is dislocated. That means number of non-metal ions are less compared to the metals. Compared to metals, so therefore such defects we call as a metal excess defects. Number of metal ions are more, so that is called as a metal excess defect. And there is a definition. And since this electron will occupy that anionic site, so it is because to maintain the electrical neutrality of the crystal. So the crystal must be electrically neutral. So for that, this electron will occupy the anionic side. So that is anionic side. So that point is called as an F center. It is an important. So in 1 marks they ask what is the F centers. So F centers, they are also called as in a color centers. F center, they are also called color centers. So F centers means the electrons will occupy a anionic site. Electrons are trapped in an anionic site. So electrons, they occupy in an anionic site. So those are called the F centers. They are called the F centers or color centers. This is also called color centers. Color centers because after this defect, the crystals show some color. So sodium chloride crystals, when it is heated in the atmosphere of sodium, so that crystal, after that defect, the sodium chloride crystal, it changes its color. Initially it is in a colorless. After that defects, that is the metal excess defects is observed in that sodium chloride crystal means, so due to the presence of these electrons, so that crystal appears as a light yellow color. So that yellow color, it is because of the F centers. It is because of the electrons present in that crystal. And also the conductivity of that sodium chloride is increases due to the presence of the electrons. So presence of that electrons, the sodium chloride conductivity is also increasing. And the color, as I told students, the color is because of this electron. So what happens is, these electrons gains the energy and get excited to a higher energy level. When it comes back to the lower energy level, it emits its energy in the form of a radiation. That radiation or that wavelength of that radiation falls under the visible region. So that's why it looks like in a color. Okay, so that's why we call it an F centers as in a color centers. Now this is about the metal excess defects. Okay, the next one we go for metal deficiency defects. Next, another one type of non-stoichiometric defects, it is the metal deficiency defects. So to explain that, I am taking example as FeO. First, let me tell you about this metal deficiency defects. So here, the number of metal ions are less compared to the non-metals. So here, iron is a metal and oxygen is a non-metal. So number of metal ions, iron, they are less compared to the non-metals. Right? When we observe such a defects in the crystals, so that defects we call it metal deficiency defects. And since these defects normally observed in case of the metals which shows a variable oxidation state. For example, transitional elements, they are showing in a variable oxidation state. And also this defect is observed in the compounds whose valence is more than 2 or more than 2. Okay. So here FeO is iron oxide. Here Fe plus 2, its valence is Fe plus 2, oxygen is minus 2. Okay. As friends, this is the formation of iron oxide. It is a perfect crystal. That means all the lattice points occupied by only iron and oxide. Okay. So during formation of this iron oxide, this is the arrangement of the constituent particles. Now friends, if there is some metal deficiency defects, for that I am removing few metal ions. For example, there are 2 metal ions, they are missing. These Fe2 ions, they are missing. Let me take, this is 1, 2 and there's the another one. So I am removing 3 Fe plus 2 ions. So I have removed this one. So these points. So these points are vacant. So here iron, it shows both the oxidation state Fe plus 2 as well as Fe plus 3. Okay. So during formation of that crystal, so instead of some of Fe plus 2 ions, they replaced by Fe plus 3 ions. So here 3 of Fe plus 2 ions, they replaced by 2 of Fe plus 3 ions. Okay. So these two are Fe plus 3 ions. Okay. Now only the 2 of these Fe plus 3 ions replaces the 3 Fe2 plus ions, which is because to maintain the electrical neutrality, because 3 Fe plus 2 ions, that means the total number of electrons here is 3 to the 6. Okay. So that is equivalent to 2 Fe plus 3 ions, that is the 3 to the 6. Okay. So the total number of electrons here is 6, so it is also 6. That means that 3 Fe plus 2 ions are equivalent to 2 Fe plus 3 ions. So here 2 Fe plus 3 ions, they replaces the 3 Fe plus 2 ions. So then it creates one anionic vacancy, one cationic vacancy. One of the lattice point is vacant because of the presence of these Fe plus 3 ions. Now the number of metal ions compared to the number of non-metal are less. Then such defects will be called as a metal deficiency defects. And since the ratio we find is then the ratio of iron and oxide, then the ratio of Fe 0.96 of O. That means the percentage of Fe is 0.96, whereas the oxide is 1. They are not in the ratio of 1:1. Okay. And also in some crystals we observe that is the iron is 0.93 and oxygen is 1. So this ratio of iron in iron oxide is in the range of 0.93 to 0.96. We cannot find a perfect crystal for iron oxide. Okay, there is some defect due to its variable oxidation state of the iron. Okay. Either we get 0.93:1 or 0.96:1. They are in the range of 0.93 to 0.96. Okay. So this is about the metal deficiency defect.